All right, so 2.8. This is the second part of our discussion of inequalities. So in 2.7, we talked about radical and absolute value inequalities. And of course, we've talked about linear inequalities earlier on. In 2.7, we really only scratched the surface. And suffice it to say, I mean, inequalities can get very complicated. And I don't mean that as a social commentary. I mean that as it relates to mathematics, inequalities can be very complicated to solve. So, although I'm sure it's true for social issues as well. But anyway, so we're really only scratching the surface here. But we will, using the techniques from this section, we will be able to go back and do some more inequalities involving radical and absolute value inequalities as well. So let's talk about polynomial and rational inequalities. These things need to be approached quite a bit differently from the way that we solve linear inequalities, right? With linear inequalities, we basically just solve them the way that we solve linear equations, but we really don't solve polynomial inequalities the same way that we solve polynomial equations. And the reason for that is if you try to follow the same logic, it ends up breaking down, okay? So the way that we would solve this, if we were just pretending that it were an equation, is we would factor, and then we would set each factor greater than or equal to 0. The problem is that getting from this step to this step doesn't work, right? Because it's not the case that just because the product of these two things is bigger than or equal to 0, that one of the things has to be bigger than or equal to 0. It could be that they're both less than 0. In fact, you would have these two cases, right? In order to get from this step, in order to finish solving, you would have to consider these two cases. So I'm not going to walk you through the details. You're welcome to read the rest of it on your own if you want. But suffice it to say that it's fairly confusing, right? And there's a better way for solving polynomial inequalities that doesn't require us to look at a whole bunch of different cases, okay? So the method that we're going to use is called the sign chart method. Some people call it the sign chart method. There might be other names for it, but I'm going to call it the sign chart method. The way that the sign chart method works is that instead of thinking, where is this thing bigger than or equal to 0, you think, where is this thing positive, right? And to answer that question, you first need to figure out where the expression changes sign. And note that wherever it changes sign, it has to equal 0. So to draw a picture, it's like imagine that you had this quadratic, and I really don't know what it looks like, but from here to here, it's positive, and from here to here, it's positive, and then in between, it's negative. But the place where it changes sign, right, from positive to negative, and then from negative to positive, the function is equal to 0, right? So we start off finding where the expression is equal to 0. And then once we've done that, we can figure out in which regions it's positive and in which regions it's negative, right? That's called the sign chart method. So let me walk you through this. Let's solve this inequality using the sign chart method, okay? So first of all, we're going to solve the corresponding equation. So I'm going to factor it. And then I'm going to say, all right, so x is -3 or x is 2. That's not the solution. Sorry, that's not the solution to the inequality. That's just where that's where this expression could change sign. So what I do now is I'm going to make a number line, and I'm going to put those numbers on it. I'm going to plot them with a closed circle because here we have an inclusive inequality, right? It's greater than or equal to 0. So I'm going to use closed circles there and there. And what this does is it splits the number line into 3 regions. And I need to figure out if this expression is positive or negative in each of these 3 regions. So to do that, I'm gonna choose a test point in each region. So if you wanted to make a chart, you could do that. I don't usually make a chart, but you can make a chart that maybe looks something like this. So you have the region from -infinity to -3, right? That's this first region over here. And then you have the region from -3 to 2. And then you have the region from 2 to infinity. And for each of these regions, you need to choose a test point. So for this region here, you could choose maybe -4 as your test point. For this region, you could choose 0. And for this region, you could choose 3, right? Any test point that's within this interval, right? And what you're going to do is you're going to plug this in. It's usually easiest to plug it into the factored version of the expression, right? So you're going to plug this into the factored version of the expression to see if the expression is positive or negative in these regions. So if I plug in -4, for example, so if I plug in -4, -4 plus 3 is -1, so it's negative. -4 minus 2 is -6, so that's negative. And a negative times a negative is going to equal a positive. I really don't care what the actual number is. I just care about what the sign is. So I know that I'm positive in this region. If I plug in 0, 0 plus 3 is positive. 0 minus 2 is negative. A positive times a negative is a negative. And if I plug in something bigger than 2, like 3, 3 plus 3 is positive. 3 minus 2 is positive. A positive times a positive is a positive. So I'm positive in this region. Now, what do I do with that information? Well, I know now that this expression is going to be positive in these two places and negative in this place. What am I looking for? Well, I'm looking for where it's bigger than or equal to 0. In other words, I'm looking for where it's positive, right? So it's positive here, and it's positive there, and that is my solution set. Okay, so that's how the sign chart method works. Let me show you another example. So we'll walk through a couple more. Okay. This one, part A, it's already set up for us. I mean, it's already been factored, you know? So if we want to figure out where this thing could change sign, it's going to happen where it's equal to 0. It's going to be equal to 0 at -3, +2, and +5, right? So a lot of the work here is already done for us because the factoring has already taken place. But we have -3, +2, +5. Now, unlike the previous problem, on this one, I'm going to plot each of these with an open circle because the inequality is strict, okay? Now I'm going to choose a test point in each of the corresponding regions. And again, you're welcome to, actually, maybe I will make a chart for this one. So interval, test point, and then sign. So I've got the interval -infinity to -3, -3 to 2, 2 to 5, and 5 to infinity. So test points in each region. For this region, I might choose like -4. Now, if I plug in -4, I'm going to have, well, I'm going to have a negative, and then I'm going to have -4 plus 3 is negative. -4 minus 2 is negative, and then it's going to be squared. And -4 minus 5 is negative. So everything's just negative. But let's see what the overall sign is here, right? So first of all, negative squared is going to be positive. Then these two negatives will combine to make a positive. But then this negative out here is going to make the overall sign negative. So I'm negative here in that region. Now if I choose something between -3 and 2, like 0, I'm going to have negative, positive, negative squared, and negative. The only thing that changed from this one to this one is that sign right there. So I think that's going to change the overall thing to be positive, right? The negative squared is going to be positive, and then these two negatives will make a positive, and then times that by a positive, you still have a positive. If we plug in something between 2 and 5, like 3, we're going to get a negative times a positive times a positive squared times a negative. What's that going to be? Well, positive squared is positive. Positive times positive is positive. Positive times negative is negative, but negative times negative is positive again. So you get a positive there. So I'm positive in this region, positive in that region. Now finally, from 5 to infinity, I could choose something like 6. If I plug in 6, I have a negative, positive, positive squared and positive. So the overall sign is going to be negative in this region. Now, what am I looking for? I'm looking for where this expression is greater than 0. I'm looking for where it's positive. That happens in these two locations. So my solution set is -3 to 2 union 2 to 5. Or if you like, you can write that using set difference. You can say, well, it's really -3 to 5, except for 2, right? Same thing. So that's the solution set there. Let me walk you through another one, part B. So again, I'm going to start off by solving the corresponding equation, right? So I'm going to solve x squared, if I move the 5x over, minus x minus 6 equals 0. So that's x minus 3 times x plus 2 equals 0. This thing is potentially going to change sign at -2 and at +3. Closed circles, right? Closed circles. Okay, so let's see. I'm not going to actually make a chart this time. I'm just going to kind of do the work in my head. If I plug in something less than -2, like -3, I'm going to have a negative here and a negative there. That's going to make a positive. If I plug in something between -2 and 3, like 0, I'm going to have a negative there and a positive there. That's going to make a negative. And if I plug in something bigger than 3, like 4, I'm going to have a positive, and that'll make a positive. I'm looking for where this thing is less than or equal to 0. So I'm looking for where it's negative. It's negative right there. So my solution set is -2 to 3. Okay. So hopefully you're kind of getting the picture here. Go ahead and pause the video and see if you can do part C on your own. Okay, my kids are making crazy noises. Let me give you my solution now. So, so you'll have to forgive the noise in the background. But so I want to solve the corresponding equation. That means I need to factor this thing. Since there are 4 terms, I'm going to factor by grouping. So if I group the first 2 terms together, I can take out an x squared. If I group the last 2 terms together, I can take out a -8. And then I can factor out an x plus 3. And I'll be left with x squared minus 8. Okay, so to finish solving this, now I would say x plus 3 equals 0. Or x squared minus 8 equals 0. That means x is -3. Or x squared is 8. Which means x would be, you take the square root of both sides, and don't forget that when you do that, you have to have a plus or minus sign on the number, right? So, because you have 2 solutions there, right? So this is, square root of 8 is 2 root 2. So this is plus or minus 2 root 2, which is about, I think it's about 1.8, let me see, or 2.8. Square root of 8 is about 2.8. Plus or minus, of course. Okay, so so let's plot those now on our number line. Okay, so so I have -3, and I have about -2.8, so I'm going to call that -2 root 2 actually though, and then I have positive 2 root 2 over here. Those are the places where this could potentially change sign. Now I'm going to figure out what the signs are in each region. Oh, maybe I should plot the points, right? Closed circles. So now let's figure out what the sign of the expression is in each of these 4 regions. If I plug in something less than -3, like -4, if I plug in -4, I'm going to get a negative here. -4 squared is 16, and 16 minus 8 is a positive 8. A negative times a positive is going to be negative. If I plug in something between -3 and -2 root 2, remember -2 root 2 is about -2.8. So something between -3 and -2.8 would be like -2.9. So if I plug in negative 2.9, negative 2.9 plus 3 is going to be positive. Negative 2.9 squared minus 8. Well, let's see. Is going to be positive, right? It's about 0.41. So, or it's exactly equal to 0.41. Anyway, so it's positive in this region. Okay. Something between negative 2 root 2 and positive 2 root 2, like 0. If I plug in 0, I'm going to get a positive there. Here I'm going to get 0 squared minus 8. That's going to give me a negative. A positive times a negative is a negative. And then finally, if I plug in something bigger than 2 root 2, 2 root 2 is about 2.8. So if I plug in something like, say, 3, I'm going to get 3 plus 3 is positive. 3 squared is 9. 9 minus 8 is 1. So that's positive. So I'm going to be positive in this region again. Okay, now what am I looking for? I'm looking for where this thing is bigger than or equal to 0. In other words, I'm looking for where it's positive. That happens there and there. So my solution set looks like negative 3 to negative 2 root 2 union 2 root 2 to infinity. Okay, be careful with the brackets and the parentheses and all of that. They need to be correct. But that's how that works. Okay, so that's polynomial inequalities. They're not terrible once you get the hang of using the sign chart. We solve rational inequalities with a sign chart as well. It's quite a bit different than the way that we solve rational equations. The way that we would solve a rational equation like this is we would multiply through by the LCD to clear the fraction. But we don't want to do that here. We don't want to do that when we're solving a rational inequality. And the reason is because since we don't know what the value of x is, it could be the case that x minus 1 is a negative number, or it could be the case that x minus 1 is a positive number. So when we multiply both sides of the equation by x minus 1, we don't know if we're multiplying through by a positive or a negative. And that's an issue, because if we're multiplying through by a negative, then the inequality needs to switch direction. If we're multiplying through by a positive, then the inequality needs to stay the same. So we could set up cases and look at different cases here, but an easier thing to do is going to be to use the sign chart method. So to use the sign chart method, we're going to move the 1 over to get this statement, and then we're going to recombine this left-hand side so that it's just a single rational expression. And then we're going to do the same thing that we did on the previous page. We're going to ask, instead of asking where the expression is greater than 0, we're going to ask, where is the expression positive? Okay, and we do that we answer that question by making a sign chart. Now, one last thing about solving rational inequalities is this. Recall that if the denominator of a rational expression is 0, then the expression is undefined. So we need to make sure that we're not including in our solution set any numbers that make the denominator 0. So we will plot those things with an open circle on our number line, regardless of whether we're using a strict inequality or an inclusive one. Okay, so let me walk you through a couple examples. I haven't been using Desmos to confirm my results, but you can do that on your own if you like. I think I will maybe later on within the next couple pages. But anyway, let's solve this inequality. So we're not going to solve this the way that we would solve the corresponding equation. What we're going to do is we're going to move the 1 over. And then we're going to combine these into a single rational expression. To do so would require me to rewrite 1 as a fraction and then get a common denominator, which in this case is going to be x minus 1, right? And then I can add the numerators, right? 2x minus x is x. 5 minus negative 1 is the same as 5 plus 1, so that's 6. And now I figure out where can this expression change sign? Well, this expression can change sign whenever the numerator or the denominator are 0, right? Where is the numerator 0? The numerator is 0 when x is negative 6, and the denominator is 0 when x is 1. So I'm going to plot those 2 points on my number line, negative 6 and 1. I'm going to plot the 1 with an open circle because it came from the denominator. Okay. I'm going to plot the negative 6 also with an open circle because the inequality is strict. Okay. So now I choose test points in each of the regions and see where the expression is positive and where it's negative. So if I plug in something less than negative 6, like negative 7, then I get negative over negative. That's going to make it positive. If I plug in something between negative 6 and 1, like 0, I'm going to get a positive over a negative. That's going to be a negative. And if I plug in something bigger than 1, like 2, I'm going to get a positive over a positive, and that's going to be a positive. So this inequality is positive in this region and in this region. That means that my solution set is negative infinity to negative 6 union 1 to infinity. Let me show you another one. Okay. This one's kind of nice because we already have a 0 on the right-hand side, so we don't have anything to move over. But we're going to have to do some factoring in order to figure out when the numerator and denominator are 0. So let's factor the numerator. I think it's going to be x plus 5 and x minus 2. The denominator, I think, is going to be x plus 3 and x plus 3. So where can this thing change sign? It can change sign at negative 5, it can change sign at positive 2, and it can change sign at negative 3. I'm going to put those on the number line in order. So first should come the negative 5, and then the negative 3, and then the positive 2. Now the negative 3 I'm going to plot with an open circle because it came from the denominator. The negative 5 and the positive 2 I'm going to plot with closed circles because they came from the numerator and the inequality is inclusive. Now I plug in test points in each region to see where the thing changes sign. So if I plug in something less than negative 6, for example, I'm going to get, or negative 5, right, like negative 6, then I'm going to get a negative, 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 negative. That's going to make a positive. If I plug in something like negative 4, so that I'm inside of this region, I'm going to get a positive, negative, negative, negative. That's going to make a negative overall. If I plug in something between negative 3 and 2, like 0, I'm going to get positive, negative, positive, positive. That's going to make a negative. And if I plug in something bigger than 2, like 3, I'm going to get positive, 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 positive. That'll make a positive. I'm looking for where this thing is less than or equal to 0. In other words, I'm looking for where it's negative, right? It's negative here and here. So my solution set is negative 5 to negative 3, union negative 3 to 2. Or if you like set difference, you could call it negative 5 to 2, except for a negative 3, right? Okay, so that's that one. And hopefully you're catching on. Go ahead and give give part C a try on your own. Give the video a pause, see if you can work it out. Okay, here's my solution. I'm going to start off moving everything over. Then I'm going to rewrite the left-hand side as a single rational expression. So distributing the 3, I'd have a 3x. So this is negative 2x minus 3x. And then I'd have a negative 3. So it's negative 15 minus negative 3. That's negative 15 plus 3. Oh, I apologize. This should be a plus. I don't know why it became a minus when I wrote it down. It should be a plus 2x. So that makes this a negative x, right? A negative x instead of a negative 5x. My apologies. Okay, now I need to factor that numerator. It's going to be x minus 4 times x plus 3. Now I'm going to plot where the expression can change sign on a number line. It can change sign at -3, 1, or 4. I'm going to plot the 1 with an open circle because it came from the denominator. I'm going to plot the -3 and the 4 with closed circles because they're from the numerator and the inequality is inclusive. Now I'm going to plug in a test point from each region to figure out where the expression is positive and where it's negative. So if I plug in -4, I'm going to get a negative, negative, negative. That makes a negative. If I plug in 0, I'm going to get negative, positive, negative. That makes it positive. If I plug in 2, I'm going to have negative, positive, positive. That makes negative. And if I plug in 5, positive, 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 and that makes it positive. Now, I'm looking for where this thing is bigger than or equal to 0. In other words, I'm looking for where it's positive. That happens here and here. So my solution set looks like -3 to 1, union 4 to infinity. Okay. Okay. So that's rational inequalities. So we've talked about all the different kinds of inequalities, right? Absolute value, radical, rational, polynomial, linear, right? So we've talked about all the different kinds of inequalities. Something that's interesting is what happens when we start combining these things. These can get really messy. But let's practice, right? So the general rule of thumb, the general strategy is when you're dealing with a radical inequality is to solve the corresponding equation. But then also keep in mind that you have some domain restrictions here, right? In fact, I'm going to take care of those first because those are kind of easy to wipe out, right? So in order for this inequality to make any sense at all, I need for these square roots to be real numbers, which means I need that their radicands, I need their radicands to be non-negative. So I need x minus 1 to be bigger than or equal to 0. And I need for x plus 54 to be bigger than or equal to 0. That means I need x to be bigger than or equal to 1. And I need for x to be bigger than or equal to -54. Well, if x is bigger than or equal to 1, then x is already going to be bigger than or equal to -54. So, so this is sort of my restriction right here. I need x to be bigger than or equal to 1 in order for this inequality to make any sense at all. So if I end up with any solutions where x is less than 1, I'm going to reject them, right? Because x has to be bigger than or equal to 1 in order for this to make sense. So that's the first thing. Now, with that out of the way, let's solve the corresponding equation. To do that, I need to isolate one of the radicals, and I think the easiest one to isolate is going to be the square root of x plus 54. So I'm going to add 1 to the other side. Then I'm going to square both sides. When I do that, I'm really thinking of this like I've written it out twice and I've foiled it. Most of the time I'm going to do this kind of thing in my head, okay? But if I FOIL this, I'm going to get 4 times x minus 1 plus 4 times square root of x minus 1 plus 4 times square root of x minus 1. That's going to be 8 times the square root of x minus 1. And then plus 4 equals, here the square root and the squared just cancel and leave me with x plus 54. Okay, so I've got 4x minus 4 plus 8 times square root x minus 1 plus 4 equals x plus 54. I'm going to clean that up a little because those things cancel. So 4x plus 8 root x minus 1 equals x plus 54. Now, I've still got a radical. I've still got a radical in this equation. So I need to isolate it and then square both sides again. So I'm going to move the 4x over. And then square both sides again. I get 64 times x minus 1 equals 9x squared. Oh, 54 times 3. And then I'm going to have that twice. So 54 times 3. 54 times 3 is 162. Times 2 is 324. So, and it's negative, right? So negative 324x. And then 54 times 54, that's 2916. Okay. Still not quite there, right? We've got 64x minus 64 equals 9x squared minus 324x plus 2916. Holy schmoly. I've got to move the 64x and the 64 over to the other side. So I'm going to get 9x squared negative 324 minus 64. That's going to be negative 388x. And then 2916 plus 64, that's going to be 2980. Right? And this equals 0. Now, I can try to factor that. Or if I'm stumped with factoring it, then I can use quadratic formula. But I think I can factor this actually, because this is 10 times 298, and 10 times 9 is 90, right? 298 plus 90 would be 388. So I feel like I can do something with this. I feel like I can get 9x. I know that it's got to be negative in both places. And I need 298 here and 9, and sorry, not 90, but 10 there. Let's see. That gives us 9x squared minus 90 minus 298. 298, negative 298 minus 90 would be negative 388, and then plus 2980. Good. So now to finish solving, I would say, 9x minus 298 is 0, or x minus 10 is 0. So that means x is 298 over 9, which is approximately 30. Well, it's exactly equal to 33.1, repeating forever. And then x minus 10 equals 0 would imply that x equals 10. Now here's the deal, though. I've finished solving this equation, but sometimes you end up with extraneous solutions, right? So let's see if either of these is extraneous, or maybe both, or maybe neither. But we have to plug them into the original equation to see. So if I plug them in here to this original equation, I'm just going to use my calculator. So if I plug in 298 over 9, I get 2 times this square root of 298 over 9 minus 1 plus 1. That equals 37 over 3. If I plug it into the right-hand side, I have square root of 298 over 9 plus 54 minus 1. So I get 37 over 3 on the left-hand side and 25 over 3 on the right-hand side. So, so this does not satisfy the original equation. Let's try x equals 10. So if I plug in 10, I get 7 on the left-hand side. And I get 7 on the right-hand side. So x equals 10 works, right? That's actually a solution. So x equals 10 is the only place where well, it's the only place where these two expressions are going to cross paths, I guess you could say, right? It's the only place where these two expressions are going to cross paths. So the next thing I need to do now is figure out, okay, so when is this expression less than that expression, right? I know that they cross paths at 10. So that means that at 10 and only at 10, right? That's the only place where they cross paths. So the question is, left of 10, is this less than that, or is this greater than that, right? So that's really the question I want to ask myself. What I'm going to do actually is make a little sign chart. And by the way, keeping in mind that x has to be bigger than or equal to 1, right? So this is like an absolute necessity, that x has to be bigger than or equal to 1. And then on the other hand, I want to figure out what's happening around 10. So let's plug in something like, I don't know, like 9. If we plug in something like 9, do we get a true statement here? Let's see. So 2 times the square root of 9 minus 1 plus 1 is about 6.7. And then on the other hand, square root of 9 plus 54 minus 1 is about 6.9. So I'm 6.7 here, 6.9 there. This is definitely less than that. So I think that my solution set's going to be going this way. Okay. And of course, both of these conditions have to be met simultaneously. So in other words, I'm taking the intersection of those two. So my solution set should be 1 to 10. Okay, that's what my solution set should be on this problem. Let's use Desmos to verify this. So we've got 2 square root of x minus 1 plus 1. And then we've got square root of x plus 54 minus 1. So this is the scenario. We're interested in knowing when the blue is less than the green. The blue, it looks like, is less than the green between -1 and 10. After 10, the blue gets larger than the green. So that confirms our suspicion. The purpose of this problem is to show you how tricky these things can be. Oh man, these things are just absolutely fraught with peril when it comes to trying to solve them. So consequently, I'm not going to test or quiz you on something like this. I would never give you this problem on a test or a quiz. But I just wanted to show you like how difficult solving inequalities really can get. However, there are other kinds of inequalities that I might give you on a test or a quiz. Like part B is a really good problem to sort of test how well you understand the information that we've covered in this section. So let's go through part B. At heart, this is an absolute value inequality. So we're going to solve it like an absolute value inequality, which requires us to first isolate the absolute value. So I'm going to add 4 to the other side. And now we have absolute value of some function is less than or equal to some positive number. And if you think back to the cases that we talked about in 2.7, then you know that what we're saying is that the absolute value of this expression is less than or equal to 3. That means that this expression can be no more than 3 units from 0 on the number line, which means the expression has to be between -3 and +3. All right? So I have this situation. Now, to solve this is a little tricky. What I'm going to do is actually split this up into 2 inequalities. Remember that this is an AND inequality. So this is like saying -3 is less than or equal to x squared plus 3x minus 18, and that that x squared plus 3x minus 18 is less than or equal to 3. So I really have those 2 inequalities that I need to solve. So I'm going to solve them separately. I'm going to add 3 on this one. And here I'm going to subtract 3. Now I'm going to solve the corresponding equations so that I can figure out where this might change sign and where this might change sign. So let's see if I can factor it. I think 5 and negative 3, x plus 5, x minus 3. Here I'm thinking, oh, can I even do this? 7 and 3 won't work. That would give me 4, right? So I think I have to use quadratic formula. What a pain. Okay. B squared minus 4 times A times C over 2A. Let me just pop that into my calculator and see what we get. So negative 3 plus square root of 9 minus 4 times negative 21. And that whole thing needs to be divided by 2. Yeah, that's nasty. That's root 93 minus 3 over 2. If I add root 93 minus 3 over 2, or if I subtract, that's negative root 93 minus 3 over 2. Holy schmoly, what a pain. I don't want to finish this problem. I don't want to finish this problem. Well, here we go. I don't even have enough room to finish the problem, to be honest. But here I can make my little number line. So I've got negative 5 and 3, and I can make my sign chart. So in this region down here, if I plug in something like negative 6, I get a negative and a negative. That makes a positive. By the way, these should be closed circles. If I plug in something between negative 5 and 3, like 0, I get positive and negative. That makes a negative. If I plug in something like 4, I get 2 positives. So, and I'm looking for where it's less than 0. So, or sorry, not less than 0. I'm looking for where 0 is less than the expression. In other words, I'm looking for where the expression is greater than 0. So that's actually in the positive regions there and there. So that's what I get from the first one. From the second one, let's see. Root 93 minus 3 over 2 is approximately 3.3. And then the negative version of that is approximately negative 6.3. So here I've got negative root 93 minus 3 over 2. And here I've got positive root 93 minus 3 over 2. And then I can make sign charts there as well. So for this one, I need to choose something less than negative 6.3, like negative 7. Right? If I plug in negative 7, I get 49 minus 21 minus, or I'm sorry, I should be plugging it in here. Yeah, 49 minus 21 minus 21, that's 7. So it's positive in this region. Is that right? If I plug in something between negative 6.3, negative 6.3 and 3.3, like 0, I would get a negative 18, so it's negative in this region. Oh yeah, of course, that's right. And then if I plug in, sorry, this was really bothering me, but no, of course that's right. And if I plug in something bigger than that, like, so something bigger than 3.3, like 4. If I plug in 4, I get 16 plus 12 minus 21. That's positive as well in that region. Okay. And I'm looking for where this thing is less than 0, though. So I'm looking for that region right there. Now, how do I put all of this together? Well, this was an and inequality, so that implies intersection. So I need to do this interval, intersect this interval. So let me put it all together onto just a single number line. I've got negative root 93 minus 3 over 2, and then I've got negative 5, and then I've got 3, and then I've got positive root 93 minus 3 over 2. And what I have is this, or I'm sorry, it's this intersect this. So the intersection is going to go from here to here, and from here to here, right? So the intersection is going to go from negative root 93 minus 3 over 2 to negative 5, and then it's going to go from 3 to root 93 minus 3 over 2. And there you go, ladies and gentlemen. What a headache, right? So these things get quite nasty. Let me give you some more examples. You're probably saying, please don't. No, please don't. But yeah, let me give you some more examples. So here, we can solve this inequality by squaring both sides. And now, what do you know? We've got this quadratic inequality. But hey, we have to be careful too, because we need for the radicand to be non-zero. So we also need x squared minus x minus 2 to be greater than or equal to 0, right? Because it's a radical inequality. Well, let's see what we get here. We've got x squared minus x minus 6 is greater than 0, and x squared minus x minus 2 is greater than or equal to 0. I guess I didn't need to write that one out again. Let's see if we can factor these now. This is x minus 3 and x plus 2. This one is x minus 2 and x plus 1. So here, it changes sign at negative 2 and at positive 3. I can choose a test point in each region. Something less than negative 2 would give me a negative times a negative. Something between negative 2 and 3 would give me a negative times a positive. And something bigger than 3 would give me a positive times a positive. Open circles, right? Since the inequality is strict. And I'm looking for where it's positive. So that's there and there. Over here, I'm going to change sign at negative 1 and at positive 2. Closed circles this time. If I plug in something less than negative 1, like negative 2, I'm going to have a negative times a negative. That makes a positive. If I plug in 0, I'm going to have a negative times a positive. That makes a negative. If I plug in something bigger than 2, I'm going to have a positive times a positive, and that makes a positive. And I'm looking for where this thing is positive. That happens here and here. Combining those solution sets now, let's see what we get. So I'm going to try to put them all on here. I'm going to start negative 2, and then I have negative 1, and then I have positive 2, and then I have positive 3. And on the one hand, I've got this scenario, and on the other hand, I've got this scenario. The intersection then is going to be there and there. Okay? So the solution set is going to be negative infinity to negative 2, union 3 to infinity. And that's that one. Whew. Okay, one more. This has been a long and very tiring section for me. One more. Oh, what do we do with this? This is similar to a polynomial inequality, right? We just have these fractional exponents, but we know how to take care of those, right? We can factor out an x plus 2. right? We've got two factors here, and they've both got a factor, or sorry, we have two terms there, and they both have a factor of x plus 2 in common. So we can take out an x plus 2 to the smallest exponent, right? -1/2. If we do that, we're going to be left with x plus 2 to the 3/2 divided by x plus 2 to the -1/2. Well, 3/2 minus -1/2, that's 3/2 plus 1/2, that's 4/2, which is 2. So we're going to be left with x plus 2 squared. And then x times x plus 2 to the -1/2 divided by x plus 2 to the -1/2 is just going to be x. Okay, so we've got x plus 2 to the -1/2 times x squared plus 4x plus 4 plus x. And that's x plus 2 to the -1/2 times x squared plus 5x plus 4. Goodness. I can factor that. And in fact, I can rewrite this as follows. So I can rewrite this as x squared plus 5x plus 4 over x plus 2 to the +1/2. I'm just going to write that as the square root of x plus 2. So let me factor now. This is x plus 4 times x plus 1 over square root x plus 2 greater than or equal to 0. Now, all kinds of things need to happen here. For one thing, we need for x plus 2 to be bigger than or equal to 0. Otherwise, it doesn't make sense to talk about this. So we need x plus 2 needs to be bigger than or equal to 0. That means x needs to be bigger than or equal to -2. So just right off the bat, right, this is a restriction that we have to reckon with. And then from there, we need to note that this thing changes sign whenever x is -4, x is -1, or when x is -2 potentially. Then again, well, let's just do that. Let's just make our sign chart. So I'm going to put -4, -2, and -1 on here. The -2 definitely needs an open circle, right? Because that comes from the denominator. The other two get closed circles. But notice that because of this restriction, right, x needs to be bigger than or equal to -2, we're not even going to take any of this stuff into account, right? Because x needs to be bigger than or equal to -2, and it can't equal -2, so actually it just needs to be strictly bigger than -2, okay? So I don't even care about this stuff. I'm just going to worry about these regions. Now I want to know where this expression is positive and where it's negative. So if I plug in something between -2 and -1, like -1.5, -1.5, I'm going to get a positive, a negative, and a positive. That's going to make a negative there. And then something bigger than -1, like 0, I'm going to have a positive, and a positive. That's going to make a positive there. I'm looking for where this thing is positive, so that happens in that region. Notice that if I tried plugging in something less than -2, I would end up with some nonsense, right? If I plugged in -3, I would get a positive, a negative, and then a non-real. So it's impossible to say if that's going to be bigger than or equal to 0. That's why this restriction comes into play, right? So really our solution set is just -1 to infinity, and that's that. So anyway, hopefully that gives you a good idea about how to solve these inequalities. You just have to keep your head and think through things kind of logically. Most of the stuff from the homework, here's your homework, by the way. I accidentally printed it out, but it kind of works well for us so that I can point out some things to you. For most of these things, for all of these, it's really straightforward, right? The solutions to like 1 through 16, 17, 18, all the way through all the way through to like 20, the solutions are really straightforward. I would say probably even 21, 22, 23, 24 are probably straightforward. Around 25 and 26, things might start to get a little bit hairy. These ones, from this point on, these are like the last 4 problems. But you only have to do the odds. So 1, 2, 3, 4, 5, 6. So you have 6 of those kinds of nasty ones to do. And they're really going to stretch your brain. Think of that as good exercise for your brain. Okay. But that's all I'm going to say about that. Thanks for tuning in, and we will see you in chapter 3.